Good morning, everyone, and welcome to the 2-Bit Circus Playful Learning Stream. My name is Kate, and today we're going to be going through the Gelatin Refraction project in our project playbook. You can find that on page number 29 today. And my best suggestion for you... Good morning, Stark Sonnet, excuse me. My best suggestion for you, if you're following along today, is that you already start your gelatin. So by following the packet of instructions that you have on your powdered gelatin that you should have, what you can do is put in some cold water into a hopefully rectangular dish, because that's the shape that we're working on today. And then you're going to tap in a thin layer of the gelatin mix. Make sure it's evenly spread across the board. And then you're going to add hot water to that. Mix it together until everything is dissolved. And then put it in your freezer, not your refrigerator. If you put your gelatin in your refrigerator, it will take a total of 8 hours to fully solidify. However, we don't have that much time. I checked on my gelatin. It was still very, very much liquid last time I checked on it. So the speed up process for that, oh, excuse me, you can hear Mr. Poe in the background. He is having a very good time with some catnip, I think. But anyways, I digress. You can put the gelatin inside of your freezer instead, and that should shorten your time to 2 hours. Hopefully it'll take less time than that. Fingers crossed. So today, Starks on it, our gelatin actually doesn't have any flavor. Gelatin is pretty flavorless by itself. The flavor that you taste whenever you have Jello or anything that has that Jello consistency, it's because it's got some sort of sugar inside of it, as well as maybe some sort of fruit powder to give you that color of red for strawberry, for example, or blue for blue raspberry. Even though a blue raspberry doesn't exist in the world, it's a popular flavor for a lot of desserts. And good morning, Mike. It's good to see you all this morning. So that's my suggestion to all of you, is that you already get ready with your gelatin, because it's going to take a long time. This project cannot be done with chocolate pudding, and I'll tell you why, Starks on it. Chocolate pudding is actually too dense. And unfortunately, the laser that we're using is not strong enough to go through, be shown through the chocolate pudding. We would have to get a really, really, really expensive laser. We'd have to get a super powered laser in order for that to happen. And you might end up actually burning the pudding instead of exploring refraction like we are today. And thanks, 2-Bit Circus. This frame's pretty great. We had one of our lovely graphic designers make this on our team, and it's wonderful. Yes, yeah, I don't want you to burn your chocolate pudding either. So maybe not. Let's not use overly powerful lasers that might set things on fire. That would be extremely sad. So the last 2 weeks, I've been talking to you all about light, and mainly reflection of light. That's what creates kaleidoscopes as well as periscopes. We're mainly focused on light reflection for those. But today we're talking about specifically, excuse me, I think I've got a cat hair. We're talking specifically about light refraction, which is different than light reflection. So I wanted to start off today with a brief overview of light again and what light is, so that we can understand it better. And then we're going to go into the different concepts of reflection, refraction, and we'll explore some other things while we're waiting for our gelatin to solidify. And we'll also talk about gelatin a little bit too, my friends. But let's get this video up and ready for you all. Super fun. Nope, that's the wrong one, Kate. Ooh, and we're going to talk about rainbows too, my friends. But let's talk about light first, because we just need a brief overview, again, of what light is. Oh no, I paused it at the wrong moment. Let's go back a little bit. Okay, so for all of you at home, this is the electromagnetic spectrum, and as you can see, we can only see a very, very small slice of the electromagnetic spectrum. Yes, there is a lot of light that we don't think about day to day. That is very true. So there are gamma rays, X-rays, ultraviolet rays, infrared rays, radar rays, FM, TV, and AM. So, for instance, X-rays, we know what those usually are. If you have a break in your bone, usually you'll go get an X-ray done to see how severe your damage is and how to heal yourself, how the doctors can help you heal by setting your bones correctly or putting it in a cast. However, when we get X-ray done, we usually have something pretty heavy and metal put on top of us, and that's to protect certain organs and other areas from the X-rays themselves, because those rays can cause damage. So we want to make sure that they don't spread everywhere and they're just being shown through the area that we want to examine where the break might be. There's UV rays, ultraviolet rays. That's usually when we think of the sun, we think of UV rays. Those are the rays that come down and shine on us. Infrared, that's usually what we talk about when we're talking about night vision or certain species, like I believe snakes and lizards, they see in infrared. Please correct me for any of you animal experts at home. Please feel free to correct me. Radar, we all know what radar is. FM is on your radio. FM is like 97.1 or 93.3. There's a bunch of different FM stations on the radio. TV, we have TV rays that have to come in, and that's what talks to your TV set and satellites and everything. And we also have AM waves, and that's on the AM radio channel inside your car. Radio is light. Not the radio itself, but the waves that it travels in is on the electromagnetic spectrum. So, in a way, the waves travel like light. Huh. You're right, Stark's on it. I'm actually going to Google that because now I'm really curious, and I'm like, wait, I've never been proposed that question before. I know, I'm with you. Light is radio? Radio is light? So, what I'm seeing right now is that sound waves are on the electromagnetic spectrum. So yes, sound is like light, but it is not light itself. It just travels in waves just like light does. So it's similar, and it lands on the electromagnetic spectrum. Stark's on it. That's what I found out for you today.
Range of
hopefully that answers your question a little bit more too in this terms of evolution. As we saw, the reason why we see this specific realm of light is because we developed it, and it's the only electromagnetic wave that you can see in water. And as we know, because of science and study and fossils, most of the primordial creatures that were created, they started off in water, so they needed to be able to see in water. And when you think about humans and most mammals, they start off in a womb. And that's usually filled with a lot of liquid. And while eyes take a while to form, and while, you're not looking around inside the womb, you're not blinking or anything like that, we still develop in this realm of water, like they were just stating on the video about those early creatures that came onto planet Earth that were created and came out of the water. They had to be able to see, and this is the only visible light to us with the human eye. It is the only electromagnetic wave that not only works on land, but also on water. But let's continue. Let me just back up because he said some really, really, really important things right there in a way that that was super, super cool. So, as you can see, this video was made in 2015, and as of that date, and still to this day, we don't have that answer as why there is a finite speed to the speed of light. It is still a mystery to us, and that is the wonderful thing about the world around us, is that we actually don't know very much about it, especially our oceans. That's where most of our knowledge is lacking when it comes to our universe, and we haven't explored a lot of these things that we know to be true. They're still a mystery to us, and that's okay, because maybe one of you watching today will get really inspired by this, and maybe you'll start trying to find and explore and experiment with these concepts to help us find the answers. But let's go over these important things about light once more.
Is a part of a spectrum, an elementary particle that also behaves like a wave, propelled.
Okay, so light is part of a spectrum. Got it. And it travels in waves. What we consider waves. It doesn't look exactly like these illustrations as you've seen in the bottom right corner. This isn't what actually these elements look like in their natural form. This is just an artist's interpretation so that we can understand it much better. Oh, and I'm glad to see that you shared this video with your students, Mike. I'm glad I can reshare it with our community right now on a larger scale. So we've got at least somebody else who votes for the quality of this video right here. Lovely, and that's a lot of what's true about science to this day, is that we're constantly in search for answers and to understand the world around us even more. Oh, and I'm so glad that Andy enjoyed the video. That means that it was engaging, and hopefully for some of you who find auditory learning a little hard, hopefully that video helped explain to you in a different or a better way than I can how these concepts work with light. So, light exists when there is not only two waveforms that travel perpendicular to each other. Remember, that's what they were just talking about. And then not only does it travel perpendicularly to each other, but it also is constantly oscillating, which means that it's constantly rotating. It's just constantly going. And that in turn turns into light. And we've been talking about a lot of light reflection lately, especially when it comes to our eyes or how we perceive color. It's because that this particular object, so for instance, my little speaker here, it's magenta, right? It's kind of fuchsia. So that means that it's absorbing every other color in the spectrum that we can see. So yellow, red, green, some blues, some purples in there. It's absorbing all of those colors and instead reflecting this fuchsia color. This is the only color it is not observing, and that reflection in turn from the light that we see, because in the dark this would just look like a black box to me because I can't see very well in the dark and most humans can't. So this box is reflecting this magenta color, and in turn for me to see it this color, my eyes and the way that they work is that it's a reflection on the back of my pupil and iris, and instead that reflection gets shown on an image on the opposite side of my pupil, and that's what I see right in front of me. A great example of a reflection, we talk about it all the time, mirrors. You know, we call it a reflection in the mirror, right? Because it's an image of yourself. Sometimes, depending on the mirror and how distant it is away from you, it can seem a little distorted. So that's where we have those fun mirrors where you can look super tall or super round or super stretched out or kind of goofy looking. That's all just different things, images being created by the different shapes that the mirror is in. Okie dokie. But today we are talking specifically about light refraction. I've got a different video for you this time on this one. And hopefully this will explain a little bit more. I think it's this. A little bit more about reflection, refraction, and absorption. So let's see. All right.
Absorbed or refracted. Let us learn these terms in detail. When light hits something and bounces off of it, we say it reflects. Reflected light is what helps us to see. We see objects only when light reflects off them. When it is dark and no light is reflecting, we cannot see anything. Some objects reflect light more than others. A shiny surface reflects a lot of light. A mirror is very shiny. That's why it reflects so much light, and we can see ourselves in it. Materials that are dull do not reflect a lot of light. They absorb, soak up, a lot of light rather than reflecting it. An old penny that has been passed around a lot has lost its luster, shininess. It is dull. In case of few materials, light does not reflect off them, but travels through them. When light travels through water, glass, plastic, or any other thick substance, it slows down. Think of how you're slowed down when you walk through water. This slowing down of the light's speed also makes it bend or refract. Have you ever noticed that when you put a straight straw into a glass of water, it looks like the straw is bent? That's the result of refraction. A thicker liquid like syrup bends the light even more. Let us now see what are transparent, translucent, and opaque objects. We can observe objects to find out how much light passes through them. Imagine you have in front of you a piece of plastic wrap, a piece of wax paper, and a piece of aluminum foil. If you held them up to the light to see how much light shone through them, what do you think you would find? The light would pass directly through the plastic wrap. Light passes easily through clear objects like glass and clear plastic. We call these objects transparent. The light would somewhat shine through the wax paper, but not completely. Few objects like stained glass windows and thinly colored plastic let some light through, but not all. They are translucent. What about the aluminum foil? Light would not pass through it. We call objects that block all light opaque. Probably most of the things around you right now are opaque. The floor, your desk, your chair, even yourself. When light hits an opaque object, it is stopped in its tracks. It cannot pass. Behind the object that blocks the light, you will see a shadow. The sun makes many shadows throughout the day as it hits trees, homes, cars, and people.
I think that's good enough of that explanation for now. So hopefully that made a little bit more sense about reflection versus refraction. And then they talked a little bit about the difference between translucent objects, transparent objects, and opaque objects. But let's break down some refraction for you right now. I just checked on my Jello. It is still very much so liquid, but I have other Jello that we can experiment with, thank goodness. But let's do the water example real quick. So if you can, get a clear cup from your pantry, if you have one. Not something like this. This is a little too translucent. You can't really see the water in here as well as you can in something that is transparent. So this glass cup in my hand is transparent, what we were talking about, that light shines through it completely. While on the other hand, this plastic cup in my hand is translucent. Translucent means that light can still go through it, which is very clear. You can still see light coming through it. I'm holding it up to my light source and you can actually see it change it. And some light still travels through. Versus an opaque object, such as my Bluetooth speaker. This is an opaque object. You can see that if I were to put it in front of a light source, it would block everything that would be coming out. So if you can, grab your transparent cup, put a little bit of water in it, make sure you have a straw with you, preferably one that's not squiggly or bendy, otherwise this experiment won't work so well. So I've got my cup here, and I'm about to put in my straw, and this is us experimenting with the idea of refraction. So let's see. All right, so you can see right now that my straw is in my cup. However, when I look at it with my human eye, it looks like the straw is actually broken. You can see, I think you can actually see it a little bit right now. It looks like the straw that is in the water is about an inch or two off from the straw that is the part of the straw that's sticking out of the water. It's actually quite cool. So that's refraction, my friends. The light is getting refracted in the water so that the straw looks like it's kind of crooked or broken, that it doesn't line up well. You can't really see it very well with the camera, but you can if I tilt it at an angle. Oh, right there, actually. That's exactly what I see. The way that I've tilted it in the camera for you is exactly what my naked eye sees. You can see that there's a gap in between where the straw is. Like, it almost looks like they're two different straws. However, we obviously know that it isn't. It's just one straw in here. But because of the way that the light is refracting inside this glass, it looks like it doesn't line up properly at all. Fascinating. Okay, so the original idea with the gelatin. By the way, we should talk about gelatin because I need to tell you what this stuff is before we start experimenting with it. Gelatin is derived from collagen. And it does have some health benefits, so eating Jello is not always bad for you. However, Jello specifically has a lot of sugar in it, while gelatin plain by itself does not. Gelatin has been shown to play a role in joint health and brain function, and it also can possibly improve the appearance of your skin and hair. So, gelatin is mainly a cooking collagen, and it's almost entirely made out of protein, which makes it not friendly to anybody who is on a vegan diet, because anybody who is vegan doesn't eat any animal byproduct. So this is vegetarian friendly, but it is not vegan friendly because it is an animal byproduct. Collagen, just so you know, is the most plentiful protein found in animals and humans. It's found almost everywhere in the body, but mainly collagen is found in the skin, the bones, tendons, and the ligaments of humans and animals. It provides strength and structure for tissues, and collagen can be extracted from those parts when we're talking about gelatin explicitly. It can be extracted from those parts by boiling them in water. And people often do that in order to make a soup stock to add flavor and nutrients. So whenever your mom is making chicken stock from scratch, this is essentially what she's doing, is she's cooking that collagen out of the bones, the skin, and whatever else may be in that pot of soup, or pot of water, excuse me, in order to make soup. And just so you know, please don't eat gelatin on its own. Why? Because it's flavorless and colorless, so it looks clear most of the time and also has no flavor on its own. And it can dissolve in warm water and has like a jelly-like texture as it cools. So gelatin is what gives Jello that kind of boing, 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 boing factor to it, that sort of the jelliness of it, that it just kind of shakes like this and keeps moving. But it doesn't break. It's able to take a lot of shaking and a lot of movement, and it's able to take that energy and disperse it instead of holding tight onto it like most other objects. So, if you didn't know, thank you for typing out boing, boing, boing for me, Starks on it. If you didn't know, gelatin actually is made in two processes. First, what you have to do is, as I said before, dilute the powder in cold water. This is also the process that happens in Jello. And then you add hot water afterwards to fully dissolve all of the gelatin particles. Miss Athena, you've been fed. We are teaching class right now. Again, for my vegans out there, it's not suitable for you because it is made out of animal parts. So, if you didn't know, as I was saying earlier, gelatin is mainly made out of protein, and that percentage is actually 98 to 99%. Gelatin is all protein, so 98 to 99%, and that's broken down into smaller sections for my super sciencey nerds out there. That's going to be glycine, proline, valine, hydroxyproline, and glutamic acid. Woo, that's a lot of words. This is why I suggest learning Latin, because it could help with the pronunciation of those words, but you can also sound it out. You don't necessarily have to know any Latin to sound out these words. But those exact amino acid compositions, they do vary depending on the type of animal tissue being used and the method of preparation, but all of those amino acids are present in gelatin. So, if you eat gelatin, as it's been studied in a few cases around the world, it can help with joint and bone health. It can also possibly help in the appearance of your skin and hair, make your hair thicker, shinier, and it might possibly improve brain function and mental health. Now, this last one has mainly been only studied once, and they just found that taking glycine significantly improved memory and certain aspects of attention. So this hasn't been studied or explored through a lot, but it's something that you might want to explore. And apparently gelatin is known to possibly help you lose weight. Some other benefits of gelatin may be that it can help you sleep a little better, and it potentially can help out with type 2 diabetes. I did not know this. Gelatin specifically, my friends, we're talking about gelatin, not Jello, because Jello has sugar in it, a lot of sugar actually, and we're just specifically talking about gelatin, the material that makes it super springy in the first place. And last but not least, it's seen mainly just in rat studies that it's improved gut health and the potential of liver damage, and it can slow cancer growth. So all these cool things about gelatin. Who knew? But again, reminder for my vegan friends out there, it is not vegan friendly. Okay, so we're going to explore how this laser light travels through Jello. So with the clear Jello, we would clearly see the red light. However, I have red Jello with me that is in its final state of solidness? Is that a word? We'll figure it out. However, it's red. So when I turn on my red laser, as you're about to see, I have this fancy dancy makeshift laser that we used for the Steam Carnival. Check it out. I believe it's still on YouTube. Okay, so as you can see, my friends, I have a red laser pointer. You can see it right there on my hand. Ooh, where'd you go? Where'd you go, friend? Where'd you go? The light still works. Where'd it go? Ooh, uh-oh. Is it too dark? Anyways, you saw it, my friends. But if I shine it through my red Jello, you're not gonna see anything because it's also red. So, let's check on our Jello again. I will be right back. I'm just gonna put the be right back up sign real fast while I go grab my Jello. But let's all check on our Jello. Let's see how it's doing. Hopefully yours is more solid than mine, but we'll see if I can work with the Jello anyways, despite it being kind of liquidy. Let's get an update. Yeah. Oh, it's a little bit more solid-ish. Coming around. All right. So, here is my clear container with my gelatin inside of it. Huzzah. And, want to make sure I don't spill this gelatin anywhere. That would be quite the tragedy. Quite the tragedy indeed. Okay, and let's see if I can get you some perspective as to what's happening with my Jello right now. I will say it usually dries clear, So I'm a little bit curious as to why my Jello seems to have gained an opaque consistency. I'm trying to find a good camera angle for you all before I change the view so you don't get sick by my GoPro being moved around. Okay, that's slightly better. Okay, there we go. That'll work. Okay, so you all can see my Jello and my workspace. Let's see if we can add a little bit more light. I know that means less light on me, but more light on the important thing that you need to see. Great. So, my Jello. My Jello is opaque. My Jello is not exactly my Jello is translucent, not transparent like we were hoping it to be. But it is translucent, and we're going to turn off the lights, try to make your area as dark as possible, like I have around my station. And oh, here is my laser. Okay. And it says, shine a laser through the gelatin. Okay. Well, let's give that a try. Let's see what it does. I think I need... Oh, you can kind of see it. Oh my goodness. I thought I saw it on the other side. Oh wait, let's see if I can do that again. I seem to be having laser problems. It's not very strong. Oh, let's see if this will work. Boop, boop. All right, it's getting dark, everyone. It's going dark because we gotta see this experiment. Oh, it's really dark for you all. Let me see if I can help you see my light. Oh my goodness, I just think my laser pointer isn't strong enough. So, as we can see, my laser is not strong enough for you to see this happen. But however, I'm gonna grab a flashlight. I'm gonna see if I can grab something else. All we need is a strong source of light. Something super piercing. So I think I have a flashlight. Haha, I do. Let's give this baby. It's one of those emergency flashlights, so it is a crank flashlight, but we'll see how this goes. So, in theory, the light should be able to travel through the Jello, which is true. Oh, yep, we find that to be true. It's kind of going through a little bit, but not all the way. I'm not quite seeing... Oh, nope. Yep, just a little bit. I can see a little bit of the light on the other side of the mirror, which I know is hard for you all to see right now. Let's see if I can... Looks like my battery is running out versus me cranking it. There we go. Okay, so you can see that. You can see the mirror on the other side of the Jello right now. And that, ooh, I've got a red light too. Ooh, you can see the red light. Hold on, let me turn this baby around. Okay, so what we are seeing is that this object is translucent enough for light to travel through, although not a lot of it. But let's see, what are we exploring today, 2-Bit? We're exploring to see if we can reflect the light back into the gelatin with this light. Okay, I don't think we can. It's barely coming off with any light as it is, but it looks like I've fully charged my red light battery right here. You can see it, all my friends. Okay, let's do it right this time. Okay, so as you can all see, you can see it going through the Jello and reflecting on the other side of the mirror. And it looks like I can reflect... Nah, No, it doesn't look like I can reflect too much back in. It is a little bit, but it's not strong enough. And I've got to keep cranking my flashlight so that we have light, my friends. So, because of the fact that this item is not as transparent as we hoped it would be, like the glass, for example, the water glass, it's not letting a lot of the light come through. So there's not a lot of light to reflect back from the mirror, and therefore there's not a great reflection. However, there is a bunch of light refraction happening. And what is light refraction again, my friends? Well, light refraction, again, is when light waves travel in straight lines through a vacuum or an empty space. But, as they say here, more interesting things happen to that light wave when they travel through other materials, like when they move from one material to another. For example, like how our body slowed down in water. That was an example we were given earlier. This is exactly like what the light is going through. So that's why we don't see as much light on the other end of this Jello, is because light refraction is happening. The light is getting slowed down, so it doesn't travel as far and it doesn't reflect as well back. Versus, I'm going to put my glass, I know you can't see it very well, but I'm putting the glass right in front of here, just that glass of water, and that's going to be a completely transparent, again, transparent, so that means it's completely see-through, transparent object. And let's see how that reflects with the mirror. Just keep cranking, just keep cranking, just keep cranking, cranking. All right, okay. Here we go, my friends. You're about to see it. So you can see how bright, much brighter that light is being reflected back to us from the water bottle. That is a really bright red light you can see right there. Versus the translucent Jello, and it's not as strong. You can see that the light is a little duller, and that's because the speed that it's traveling at has been slowed down by the gelatin itself. Let's turn off our light. Save that for another time. So, if you can, if you have some parents to help you out or an extra set of hands, I would love for you to measure those angles that you can make that possibly reflect back into your gelatin and see what angles they are. See if you get closer to 180, how that's like, versus something smaller like a 45-degree angle and then a 90. And see how far into the gelatin mold you can shine your light or your laser, if you happen to have one, before it dies away. Well, with this particular source of light that we see right here, I'm going to just go back to our dark camera, just because it was a really great way for us to see what was happening. Oh, here's a bright light. This will work great. So, as you can see, the closer I get to the gelatin, the more light there is. However, the further I go back, the less light there is. You almost can't even see a reflection, but you can when I'm next to the Jello. Or the gelatin, excuse me. Oh, and my light died. So, to wrap that all up, transparent objects allow light to travel at its original speed, so you can see it very clearly and you can get reflections back off of very shiny objects. However, if you are shining light through a translucent object, it is being slowed down because of the two different materials or the different densities that the light has to now travel through, so it slows itself down. And in that way, light looks dimmer or darker to us versus it going through at the speed, its original speed, and being just as bright. So, for instance, my light right now is on, and there's nothing in the way. This could be considered, I'm going to put the cup that we were playing with right in front of the light. And as you can see, not much has changed, especially when I take out the straw. Not much has changed. You might see a little bit more of a reflection of the water on my face, but the light is still the same. However, let me now try a translucent object like the Jello. I'm going to just carry you around. Woohoo! All right, and let's put that in front of my light source. Oh, well, that completely changed it. It looks a little darker, a little bit more romantic. It's a lot of soft lighting, so it's diffused in a way that looks a little softer, not so bright. So this is very bright, very stark. As you can see, I'm a little bit blown out, which means that there's a lot of light shining on my face, so you can't really see the definitions of my bones or anything. Versus if I put the translucent Jello in front of it, you can see everything. I haven't moved direction-wise. I'm in the same spot, but you can see more of me, and it actually looks pretty nice. It's a very nice glow. Now, let me put an opaque object over our light. And opaque means that no light can come through. It blocks it entirely. Well, that's a complete difference from no light to light. Again, no light, opaque object, transparent object. So all the light is coming through on the transparent object. However, opaque objects cut it out, and translucent objects filter less through because it's got to go through that material in order to travel to whatever source it needs to light on. So if any of you are a big fan of photography or know any photographers, the best example of what they have are called films or gels. They're either colored like purple, blue, red, or sometimes it's wax paper, so paper that has a little bit of a film on it to make the lights less bright. And they use those translucent pieces in order to create the sort of light that they like and have control over the art that they create. Or they might just turn off the light completely or cover it completely with an opaque object, a solid object like we talked about before, that doesn't let in light, and that will cut off all light entirely. So, refraction. Refraction today, as we were talking about it, refraction is when the speed of light, but the speed of it specifically, the way it travels in those waves, go through a vacuum or an empty space, and it gets slowed down. The denser that object is, the harder it is for those light waves to travel through, so they slow down. So that wave bend that happens in the light wave is what they refer to as refraction. So kind of like a hinge or a door. Why does this happen? Well, the speed of light is always the same, but that's only true when light travels in a vacuum or an empty space. In fact, light travels slowly in some materials more than others. And the more slowly the light wave travels through something, for instance, it travels more slowly in water than it does in air. The light wave slows down, and when it moves from air to water, and let me say that again. When it travels from air to water, the light waves slow down. When it travels from water to air, the light waves speed up. And as we saw before, that's what causes the straw to look bent in this water. And that, my friends, is refraction. And it's extremely useful, especially if you wear eyeglasses. I do for myself because I have really poor distance vision. But the lenses that are inside your eyeglasses they actually have curved pieces of glass inside. And those that bend refracts the light from the things that you're looking at. And when that light is bended, it seems for the, bending the light makes it seem like the object is nearer or further away from you, depending on the kind of lenses that you have. And that corrects the problem that you have with your sight currently. And also, you can see refractive lenses inside binoculars, telescopes, cameras, night vision goggles, and a lot of other things that you can experiment at home. Those are refractive tools that we use to make objects that seem very, very far away seem more up close. That's why you can see planets in telescopes and birds that are far away, or small bugs in binoculars, or for instance, night vision goggles. We can see in the dark all of a sudden versus seeing everything as just massive big black shapes. And if we just happen to see details in the dark is because there's some light there. But if it were to be pitch black, we would see nothing. Absolutely nothing. So, to end up today's talk, I wanted to talk a little bit about rainbows, because rainbows are a part of this natural phenomena with light. So let's talk a little bit about rainbows real fast before I have to let you all go today.
Rainbows are only seen in special weather conditions. The sun must be shining behind you, and there must be water in the air in front of you. This water is usually rain, but could also be something like a waterfall. The rainbow will then be in front of you, and it will be centered around your shadow. As you can see, it's a beautiful colored arch made up of 7 different colors. These colors are red, orange, yellow, green, blue, indigo, and violet. They always appear in the same order in the rainbow. Sometimes it's hard to see indigo and violet as separate colors because they merge into purple. Can you think of a way of remembering the order of the colors? The first letter from each color is in the order of R, O, Y, G, B, I, V. We had a think and came up with Rainbows Over Your Garden, Brief in Visiting.
All right, so that's the best way to remember rainbows. And the color that it always is in is rainbows over your garden, brief in visiting. So red, orange, yellow, green, blue, indigo, and violet. And as they just said, it is very difficult to see the difference between indigo and violet sometimes because they just seem like the same shade of purple. However, you can see with indigo, it actually has more blue. Light is able to travel through, but it goes through a sort of a tough journey, and it struggles a little bit when it comes to traveling through that object because it's going through a different matter. Then we call that object translucent instead because it does slow down that particle wave. Last but not least, we have opaque objects, and opaque objects cut out all forms of light, which means that there is no light at all. There's nothing. It's almost like the lights are off. When light is shown into water and a straight object is inserted into that transparent water, light refracts because of the difference between light traveling through air and light traveling through water, because it slows down while it's traveling through water, creates this optical illusion where it looks like the straight straw is actually bent or broken in half. And that is because of the refraction and the fact that light travels faster through air than it does through water. Well, that's the wrap up for today, my friends. That is our class on light as well as refraction and the difference between transparency, translucency, and opaqueness. These are all different things that affect us on a regular basis and controls the amount of light that we see around us. Before I leave you all, I do want to give you these fun facts. Gelatin's spring-like molecule structure swells in cold water, and then it dissolves in hot water, and that's how it solidifies. Gelatin is also a simple and effective way to keep your hair, skin, nails, and teeth healthy, as we said before. But not Jello, just gelatin itself. And last but not least, my friends, I don't know if you knew this, but laser is actually an acronym, which means that it is a bunch of letters that are put together that stand for something longer. So a laser's real title is actually a light amplification by stimulated emission of radiation device. That's what laser stands for. Light amplification by stimulated emission of a radiation. And that, my friends, is a laser. Thank you so much for joining me today. I had an absolute wonderful time with you all. Join us tomorrow again at 10 a.m. Pacific Standard Time for our awesome weekly meeting with Kane. I'm sure he'll come up with something as amazing as always. Thank you so much from me, Kate, from the 2-Bit Circus. If you liked any of the activities we did today or in the past, please feel free to check us out on www.2bitcircus.org in order to find our playbooks as well as material kits that you can order now and start following us along at home. It's been an absolute pleasure and honor, and I will see you all next Tuesday for our class on, I believe it is bottle flute. So we're going to get some musical instruments in next time. But that's it from me. I hope you have a wonderful rest of your day. Goodbye.
Good stream.